the CLT of this guy will help us build our conflict interval, right? And this guy multiplied by n, root n, will convert to a normal random variable with mean 0. Here the mean 0 is a vector form because it's k dimension. And the variance of it is the gradient of g at the true values times the sigma, which is the covariance matrix, times the gradient transpose. Why? See this? This is a two-dimensional case. I didn't prove it. I mean, if you do this for the k dimension, you will see. Right? Gradient, covariance matrix, gradient transpose. Okay. So I didn't prove it. It's the same thing. But you don't know this mu. Right now is a true value. Is a vector of the true values of the means, and you don't know sigma, which is the true value of the covariance matrix. You do your best, right? You estimate them by adding a hat. Right? So basically you have to use your samples, k dimension but n copies, to estimate each component in the covariance matrix, the sigma ij. Right? So you pair them in the right way, right? Make sense? So this is, now we know what to do with these guys. This guy, I think I have homework problems here, you know. Of course, you have to compute some derivative of this function, and so and such. Right? So you see, this tool is pretty powerful because we're able to construct conflict interval for non-expectation quantities now. Right? Interesting, right? So this is pretty powerful, right? Basically, a smooth function, the conflict interval for smooth function of expectation, or expectations, right? Plural, right? All right, I think I'm gonna, yeah. I'll cover the next two pages. Probably we should stop. Okay. So let me quickly talk about how to estimate quantile. There are many things to estimate sometimes. It's not only expectation you want to estimate. You may want to estimate variance, you may want to estimate correlation, and we'll talk about that. They fall into a they fall into a class of a smooth function of expectation. What if you want to estimate quantile, which cannot be expressed as a smooth function of expectation? So what is quantile here? This is a box plot. Quantile is an important performance metric. What is quantile? The alpha quantile of a random variable x is given by q alpha, that is the inverse function of the CDF at alpha, meaning find a q that cuts your distribution at a point so that the resulting area under that PDF is alpha. I mean, to be precise, it should be greater than or equal to alpha, but if you have a smooth f, it's going to be equality, right? That's quantile, right? This is sort of the z alpha that we've been talking about, right? Okay. Empirical distribution. So you don't know, I mean, you don't really know. I mean, if you do know this F inverse, easy, right? You just compute this, right? You compute it. You don't have to do simulation. But you don't know this in general. You're able to generate X. You're generating X not using inverse transform. If you can do inverse transform, that means you know F and you just invert it, right? Many random variables you have to estimate without inverse transform, such as, you know, how long does it take until the system breaks down? You don't know the CDF. You do know the CDF, you don't have to worry about this discrete event simulation. You just, you know, do what you have to do. So, how do we approximate the CDF? Where you approximate the true CDF by the empirical distribution. So, generating n copies of random variable x using whatever algorithm, ID copies. Count the ones. What one? Each indicator is 1 if random variable copy I is less than x, x is fixed. So x will vary later. We're estimating a function now as a function of x. Right? This gives me a proportion or fraction of samples less than x. This guy will converge to the true value of the CDF at x when n is large enough, because why does this conversion hold? First of all, intuitively, does it make sense to do this? You generate ID samples, you cut it off at a point, right? X, you fix X, you're computing the proportion of the sample points, these points, they're less than X. do they give you an estimate of the probability a random variable is less than x? Intuitively, yes, right? And when n is large enough, you should convert, this quantity should converge to the true CDF. So it's called an empirical distribution, but it's actually an approximate formula for the true distribution. But why does this converge? Hold. What is the supporting theory here? Strong law of large number. Because you're adding ID terms, call this yi, right? This guy converts to EYI. EYI is the probability of this event. Probability x is less than x. That is exactly the CDF, right? So this error is valid due to strong law of large number. Okay. Using the empirical distribution, you can estimate the quantile. Basically, instead of inverting the true CDF, you invert the empirical CDF. How do you do that, right? Sort the ID sample x in the ascending order. Basically, it's sort of an order statistic kind of thing, right? And set Q alpha, which is the estimator of the Q alpha. The big Q alpha with sample n is an approximate, it's an estimator for small Q alpha. If you pick the value, the sample, which sample? The n alpha sample. The n alpha is just the integer part, I mean the floor, the steel part of n alpha. This is not necessarily integer though. Right? You sort them, you want this many to be, to have you an alpha, then you're right? Because you pick a value which is one of the point on the x-axis, which is a cutoff, because on the right hand side, on the left hand side, they give you alpha and 1 minus alpha. Make sense? This is just like inverting, right? This is just inverting. Looking for an x value, achieving a alpha 1 minus alpha partition on the right, on the y, right? Make sense? The thing is, this can be an estimator, but what about common interval? What about the plus minus, right? How do you know n is large enough, right? So again, in simulation, if in your papers or in your research, I'm doing simulation. If you say I'm doing simulation, if you only provide a number, it's meaningless. You need to provide plus minus. You need to tell this is 95%, 99%. What is your confidence level? Okay, you have to have a number plus minus. All right. So you need a CLT, right? There is a CLT. The CLT is always in the format that your estimator converges first. Why it converges? I mean, it's easy to prove, just like this one. It converges, okay, so the error goes to 0, and you multiply it, and it's going to convert to a normal random variable with a mean 0 and a variance, which is the function in terms of stuff. Okay. There's a CLT which we don't prove, but it's easy, right? It's given in the literature. So the 1 minus alpha% common interval is given by this estimator plus minus the root of this thing divided by root n. The issue here is you can approximate the Q alpha by big Q alpha n. How do you know the density here? This F is the true density of big F. You don't even know big F, how do you know small f? Right? If you happen to know small f, you're fine. Otherwise, you usually cannot build your common interval using this. Okay, so how do we do this? I'll just finish this page, then we should stop. Okay. Issue, right? What is PDF? Small f is an unknown, and which is most of the case, right? Most of the practical case, we don't know PDF, because you don't even know CDF. Cut n, so n is your simulation budget, let's say it's a million times. Cut n into NID sample into m sections, this is called a sectioning. M is ranging from 10 to 30, so let's say m is 30. M is relatively small compared to n. N is a million or so. Each section contains n over m many ID samples. No problem, right? Let Q and I be an estimator of the quantile in the ith section using these many samples. So each section has n over m many samples, which is still long enough, big enough. You use them to estimate your Q and I. Based on all okay, right? So based on all samples in ith section, I can estimate. I have a normal distribution. So Q and I is approximately normal with a mean Q alpha and a variance what? Sigma squared over n/n. So why is this, right? Q and I minus Q alpha should converge to a normal distribution. So move the Q alpha to the other side. It's going to be a normal with not zero mean though, with a mean that is the true value, right? And this variance is unknown, right? Okay. You have m sections that are I and D. You use the m sections, right? So each Q and I is an estimator within the section, from 1 to n. You take an average of those Q and I, you get a sample mean of the different sections. That's your estimator. And the variance can be estimated by looking at the fluctuation of this Q and I in the m section. You're using a m square, so using m samples to estimate the variance. When n is large, these guys are ID, so the sample mean within each sample, each section, they're ID random variables, and they're approximately normal. It's actually a t distribution. So the confidence interval, the confidence interval is given by the estimator here, plus minus a t distribution. You don't have to worry about what is the specific structure of the variance. You just estimate the variance, right? Before we talk about what is the variance, and variance is in terms of function. Sometimes it's a function, like a small f, which we don't know. Don't worry about that, right? Let's just estimate the variance. You know this guy will be square root of the variance divided by the number of sections. So let's just estimate as m squared by working on the m samples, to the sample variance of it. In this class we don't really we don't usually distinguish the t or z, which we can use t, we can use z. One n is large enough, they're similar. So it doesn't matter. I don't want to get into just to add value. This is better or the other better, but this is the sectioning method, which can be very general, not really restricted to quantile estimation. It can be used for other estimation as well. You see, this estimation does not really depend on the structure of the variance. You just do it. Then you use your batches or sections to estimate the variance. We're going to talk about output analysis for non-terminating simulations next time. So we finished half of this, more than half of this. Then we're going to continue on Monday. Yeah, we should stop now.
So Professor, when m is less, let's say 10 or something.
Yeah.
So at that